So waves are a motion of a disturbance, and we talked about this in our waves section. And the source of all wave motion is a vibration. So we're disturbing a medium. Um, at least up in this point, we've looked at things disturbing a medium like air or water or a slinky or a string, a lot of different things that material things. So, we've looked at a lot of different kinds of waves. We looked at sound waves. We've looked at a variety of mechanical waves. We've looked at ocean waves. A lot of things with waves. It's important to distinguish the two different kinds of waves categories of waves. We looked at longitudinal and we looked at transverse, but in the past, this is another category that we need to concentrate on as well. Spherical versus cylindrical wavefronts. If you look at the one on the left, this might, help you recall something like maybe like a wave in the ocean or the beaker. You dip your finger in the water in the beaker, you see the wave go out cylindrically like that. And we've also looked at waves that are point sources. For instance, sound coming out of a speaker as a point source. If I'm talking and I'm not facing you, you can still hear me because my sound is going out spherically. And so, it's important to distinguish between these two, and understand, what's happening with each. With a point source, we know that sound goes out spherically, and we also know that light goes out spherically. And so, 4 pi r squared is the surface area of a sphere. So, if you double the distance away from either of these sources, it's going to be 1/4 as strong because it's a matter of r squared. It's an inverse squared relationship as it spreads out. In this clip, if you want to copy the URL, you can see the motion of the water going through a tank that they make for testing, and you'll see those wavefronts go through there. Wavefronts and waves are important to distinguish. If you're looking at a two-dimensional wave, if you look at the picture in the top here, and the wave is going from left to right in this case, right? The crests are right here, the troughs are right here, and the wave fronts are perpendicular to the motion of the wave in this case, right? So if you look at these magenta or pink planes, they're going right through the crests, and with the caption here, surfaces through crests and normal to the direction of energy propagation of the wave are called wavefronts. Rays are mathematical lines perpendicular to the wavefronts and give the direction of energy transfer. And so, look at the definition here. A wavefront is the surface through crest and normal to the direction of the energy of the transfer of the wave. Lines in the direction of the energy transfer of the wave, and hence normal to the wavefronts are called rays. And so we can see the ray here, going from left to right. And then we can see, the wavefronts. Each of these, a full wavelength away here from a wavefront to a wavefront. Okay, so if we consider a light bulb, and let's say this is a 100-watt light bulb, what this means is every second, 200 joules of energy is emitted. And that's what a watt is, right? It's a joule per second, how many joules per second. And so if we look at let's say this light is going out spherically, as the light spreads out, the intensity gets less and less and less as it gets further out. And it spreads out spherically according to this equation, right? The power of the source gets spread out by the surface area of the sphere because this is going out, as a sphere in all dimensions or all directions. And so, we get in a certain intensity. So let's say that we have a 400-watt light bulb. We're 3 meters away from it. Go ahead and calculate the intensity at that particular spot. In fact, this would be the same as the intensity if you were 3 meters away, somewhere around here or somewhere around here, right? Anywhere along that sphere around. So go ahead and calculate that and pause the clip, and when you're ready to check, you can hit play to continue. Okay, so we take our power divided by the surface area of the sphere. The intensity of that light will be 3.537 watts per meter. Another unit for intensity in terms of light intensity is lux. When we looked at sound, we just left it as a watt per meter squared in terms of intensity, but there is actually a special unit for it, and it is lux for intensity of light. All right, so let's say that the average power of the sun is 4.7 times 10 to the 25th watts, and we're an average distance of 149.6 million kilometers away. On 1 square meter of Earth, assuming no atmosphere, what would the intensity of the light be coming from the sun? So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so we take that power. We're going to need to figure out how many meters away we are, and we should get 167.119 watts per meter squared on 1 square meter of Earth. So in other words, on 1 square meter of Earth, in every second, we get 167.119 joules. That's what that would mean. So if you look on your data booklet under section 4.3, you'll see a section for wave characteristics. And we're going to focus here on these two right now. We're going to focus on this one later when we're talking about light and more specifically polarization. But let's take a look at these first two. Here's some cylindrical wave fronts, in this clip here, that if you want to take a look at that. Let's go ahead in this one and compare the amplitude of a 0.5 meter amplitude wave compared to a 1.5 meter amplitude wave. So we'll compare the two. So if we look at this, right, the 1.5 meter wave and a 0.5 meter amplitude wave, we know that the intensity of the wave is directly proportional to the amplitude squared. And that's what we're going to focus on here. So, how much more intensity does this wave have than this wave? If you've ever been to the beach, and especially if it's, there's a storm out in the Atlantic, the waves can get pretty huge, and the intensity of those waves really increase with amplitude. And so if we look at this relationship, right, it's a squared relationship. So we have 0.5 squared, 1.5 squared, 0.25 versus 2.25. And so if we compare these two, it's actually 9 times as intense. If you look at the amplitude, this is 3 times the amplitude. And because it's 3 times the amplitude, that is, squared, and so it's going to be 9 times the intensity. All right, so let's say we have this sailboat, and we have a amplitude of 27 meters for this wave and 13 meters for this wave. So pretty extreme at any rate. So how do the amplitudes, or how does the intensity compare? So I'm going to let you try this one. Go ahead and pause the clip and use the relationship there with intensity to figure out what's going on. So go ahead and pause the clip and do that, and then when you're ready to check, you can hit play to continue. Okay, so we've got 27 squared, 13 squared is the amplitude, and we get the ratio 729 to 169. It'd be 4.3 times greater, and so the intensity of that wave versus the other one would be 4.3 times greater intensity. So what kind of waves require a medium? And so the waves that we've looked at, they're mechanical waves. And so we've looked at a lot of different kinds of mechanical waves, and they can fall under the categories of transverse and longitudinal. And it's important to remember the distinction between those. If you remember, with a transverse wave, the movement of the particles are perpendicular to the wave motion. So the direction of the energy is from left to right, but then the particles are moving up and down in this case. This is in contrast to a longitudinal wave. Let's say the the energy is going from left to right, and then the particle moves back and forth, so it's parallel. The particle movement is parallel to the wave motion. It's also important to remember with reflection with a wave. And so if a wave hits a fixed end, the wave is inverted and it's 180 degrees out of phase. If it's open end, the energy of that wave can travel up and then down and send it back. And so the energy of that wave is, in the reflection, it keeps the same phase, so 0 degrees.